Hi guys! This video is the third part of the three-part lecture on the topic Area of a Plane Region and Arc Length. In this video, we're going to be finding lengths of curves using the definite integral. Now without further ado, let's begin. For this topic, we are going to be assuming that our curve is smooth. And when I say smooth, it means that the derivative of my function f is continuous on AB. And in AB, I mean that it should be continuous as well on the endpoints A and B. In case that the curve is not smooth, then we are not assured the technique that we will be using here can be applied. So it's very important that we always see if the function will be smooth. In case that it is left to find out on how to get the length of arc. We will be using here the technique of partitioning which we used in finding the area as well. Now, for example, I have a curve here, y equal to f of x from A to B. If I partition my x into delta x's, I'll be able to make small points here, in this case, x sub 0, x sub 1, x sub 2, and so on and so forth. You will see here that each length here is not always the same, but the lengths at the bottom will always be the same because we divided the interval into equal length. We will have endpoints for each of the arc, namely xi, yi, and xi plus 1, yi plus 1. Now what we will be doing here is the following. Since it's very hard to find the arc length of a curve, we're going to be finding the arc length of the line segment connecting each of the endpoints of the arc. In this case, since the line segment is a straight line segment, I can use the distance formula, which is given here. It means that if I add all the distances d sub I will have an approximate value for the arc length. However, this does not easily translate to an integral because we need to find a dx or a dy. For that, we will be manipulating this distance formula. For 1, I can just let delta x to be x sub I plus 1 minus x sub I, and delta yi to be just the change in y. Do note that the delta x does not change for any x sub I plus 1 and xi, but the delta y will change depending on the x sub I, and thus we will have a sub I here. Nonetheless, since the distance will be given by this formula here, by plugging in delta x, I will have a much simpler quantity delta x squared plus delta y sub I squared. The next part will be multiplying delta x squared on the numerator and denominator. And by doing so and simplifying this part here, I will have a square root of 1 plus delta y sub I over x squared, and the square root of the square will just be delta x because delta x is a positive number. And thus meaning that if I want to find the approximate value for my length, I will just need to sum all of these distances, and that's just the sum of a kind of a long formula. And if I let n go to infinity, what will happen is that these points will be closer to each other, and the line segment will be a better approximate of the curve. And thus, from an approximate, it becomes an equal, and we will have the following quantity. This translates to an integral, and that integral is given by this, where the delta x that we multiplied before will become our dx, and I have a square root of 1 plus dy over dx squared. Let's put this into a definition. If I have a smooth curve, then the length of arc of that curve from A to B is given by this formula here, integral from A to B, square root of 1 plus f prime of x squared dx. And this also explains why smoothness is an important assumption here. Because if f is not smooth or the curve is not smooth, we are not assured that f prime is continuous. and thus integrability is also in question. Since we can do this in the variable x, we can also do this in the variable y. Now, unlike areas, there is no horizontal or vertical analysis here, and that means we do not make rectangles. There is also no two functions here, f and g. Whenever we use arc length, it's much simpler because we only use a single function. And we do not need to worry about rectangles anymore. We just need to know what variable to use given the function that we have. A very good indicator of what variable to use is the isolation. If y is isolated, then that will mean that the function that you will use is in terms of x. And if x is isolated, it's better to use y. For example, if I have the following length curve y equal to 1/3 x squared plus 2 to the 3 halves, you will see that this is good. This is easily set up in terms of x because y is isolated. Now, for the purposes of the viewers, I will be placing here on the left side of the screen the formula that we had before so that we can easily remember it. Now, since we will be using the variable x, we'll be first finding out the interval AB. It's very clear here that we want the curve from x equal to 1 to x equal to 2. It's important that the value of a is smaller than b, otherwise you will have a negative value. In this case, the interval will be 1 to 2, and we just need to find the integrand. Now, unlike before in the area where it's easy to plug in f minus the g, for length of arc, sometimes we need to simplify a lot before we set it up. For example, there are a lot of steps to get the integrand. First, we find dy over dx, which is just 1/2 square root of x squared plus 2 times 2x, which can be simplified to x square root of x squared plus 2. This may look bad, but this is not enough since we still need to square it, and the square will be this, which we still need to add to 1 and then take the square root so that we'll be able to find the arc length. Most of the time, the function or the integrand of an arc length is not that beautiful because it has a square root. Though in this case, this is easily integrable, especially if you note that the integrand or the radicand 1 plus x to the 4 plus 2x squared is a perfect square trinomial, x squared plus 1 squared. Since the square root of a square can be simplified to an absolute value, it now becomes a simple absolute value integral. X squared plus 1 is always positive, and that means its absolute value is itself. And by anti-differentiating and simplifying, you will get the answer 10 over 3. Something to remember here is that the units here is not squared. Unlike area where we put square units, for length of arc, it's just units because this is a one-dimensional quantity. Let's have another example. I want to set up the definite integral for this curve. Now, since I only need to set it up, I don't really need to do all the simplification as I have done in the previous example. So it suffices that I memorize my formula well. I see here easily that since x is isolated and this is a complicated quantity of y, then maybe y is the better variable to use. So I will need to find the interval or the a and b here. Clearly, these are y values. How to get them is similar to the one in area, and that is to get the lowest value of y. In this case, that will be -1, and the highest value, which is 2. Also, we need to find the integrand. In this case, I'll just need to get the derivative, which is just a 2y minus 1. Plugging this, then I'll have a -1 to 2 square root of 1 plus 4 times y minus 1 squared. Of course, I have a dy here. One of the most common mistakes in this topic is forgetting the formula, especially the square. So remember, you differentiate, You square, you add to 1, and then you take the square root, giving you 4 operations all in all. Now, unlike area where you can easily switch from x to y and vice versa, a weird part of arc length is that it's not always the case where you can switch techniques. For example, in this particular problem, we cannot set this up using x. The reason why is because if you differentiate this and you get dy over dx, what will happen is that the dy over dx will be a 1 over 2 y minus 1. This is not that great because we want this to be in terms of x. So putting it in terms of x, you will have a 1 over plus minus 2 square root of x plus 4. This is bad for two main reasons. Number one, we have a plus minus. It means that if you will set this up in terms of x, you need to split it up at this point. But the worst part here is because at x equal to negative 4, the denominator will become 0, and that will mean that the derivative does not exist. It actually means that the function that we have here is not smooth, and thus the technique cannot be applied. So we need to be very careful whenever we have these quantities. And this is the reason why whenever something is isolated, especially a square, it is much better to use the variable that is squared rather than the linear one. Primarily because the moment you have plus minus and you have a denominator as a derivative, automatically, or not automatically, but most of the time, the technique cannot be applied. Now let's have one last example, and this is what we call a perimeter problem, because we want to find the perimeter of the region. In this case, this is the region that I'm talking about. I have three curves here, L1, you have another L2, and L3. And thus, since I can only deal with one function at a time, I will find the perimeter by finding the lengths of arcs of each of these curves. Let's start with L1. L1 is just a line. It's actually a horizontal line. And because a horizontal line can be measured by just right minus left, the x value here is 1, the x value here is negative 1, so the L1 is just 2. For L2, you have this curve here. This curve is the cubic polynomial. And you will see that y is already isolated, so that means this is good in terms of x. Just like before, I will look at the limits of x here. Since I started here, the x value is 0. I ended here, x value 1. So this will be from 0 to 1. And then I'll have a square root now of 1 plus. I'll get the derivative of this. It's already isolated, so dy over dx will just be 3x squared. And then I square it. Of course, I don't forget the dx to indicate that I am integrating with respect to x. This is similar to L3. For L3, you will see that x is isolated, so that means this is good to set up in terms of y. So in terms of y, I will have the limits, lower limit here, which is 1/2 to 3/2, so that will be 1/2 to 3/2. You still have a square root of a 1 plus. The derivative now, or the dx over dy, will just be the derivative of this, which is negative 2y minus 1/2. I square that, I place a dy to know that I am integrating this with respect to y. And clearly, since this is only a setup problem, the perimeter will just be the sum of all of this. Now in conclusion, arc length is much simpler than area. For one, there's only one function to talk about. For another, we don't need to talk about the vertical and horizontal rectangles. We just need to remember, one, the formula, all parts, including the square, the derivative, the 1 plus, and the square root. Another one is that we cannot easily just switch x and y. We need to ascertain that in the interval that we have, for example, in 0 to 1, 9x to the 4th will always exist. Otherwise, if this does not always exist, then automatically you cannot apply the technique. And now that ends our topic for areas and arc length. In the next videos, we're going to be talking about more applications of integrals, and that includes volumes. Now, I hope you enjoyed this video. Stay safe, stay healthy.